So let's start with our next chapter. Remind me, what was our last chapter all about? Chapter 8, it was all about parallel lines. And we had our parallel postulate. What was our parallel postulate?
There's only one parallel line. There's only one line through a point.
Yeah, given a line and a point not on the line, there's only one line we can draw through that. Well, we proved that there is at least one, so we can now say there's one and only one line through that point parallel to the given line. Right? That was our parallel postulate. And now, today, we're going to be using parallel lines a lot to talk about similarity. In particular, to talk about triangles being similar. Now, what does it mean, intuitively, for two shapes to be similar? So, here's a triangle and here's a triangle. I tried to draw them so that they were similar. What does it mean for two shapes to be similar?
It means you can scale one to the other.
Right, one's like a scaling up or scaling down of the other. This one, if you scaled it up, it would give us this one, or if you scaled it down, it would give us that one, right? What do we notice about those two triangles? Tell me concrete properties that they have.
Those just.
Yeah, sure.
The angles are congruent.
The angles are going to be congruent. That angle is the same size as that angle. Like within the error of my picture, right? That angle was meant to be drawn the same big as that angle. And that angle was meant to be drawn the same big as that angle. If for similar shapes, that's always going to be the case. The angles are all going to be congruent to each other. The second thing that we're going to notice about similar shapes is it's not just enough that their angles are congruent. For example, are these two shapes similar?
No.
All these angles are congruent to those angles. Right? They're all right angles.
It's not that it's
So,
They're different.
yeah, so they're not similar, and we understand that they shouldn't be similar. What's the other property we want them to have?
Same like side or same.
same ratio.
Same ratio of sides, same proportionality of sides.
Exactly.
If this side is twice as big as that side, then this side has to be twice as big as that side. Which in this case it's not. If I drew some other triangle now, or some other rectangle now, forgive the picture, but if that side's twice as big as that side, then this side has to be twice as big as that side side has to be twice as big as that side has to be twice as big as that side. And that's exactly what it's going to mean for two shapes to be similar. All their angles are congruent to each other, and all their sides are proportional to each other. That's going to be the language, and we'll define exactly what we mean by these things. We've already defined exactly what it means for two angles to be congruent. So what remains to be discussed is what it means for all their sides to be proportional. Make sense? So that's big picture what this chapter is all about. Proportional, similar triangles, and things we can prove with similar triangles. Okay. So the first theorem that we're going to have to prove, this is one that's not in the book. I don't know why the author doesn't do it. He just assumes it. So quick standalone theorem. We're going to prove that the opposite sides of a parallelogram are congruent to each other. What do I mean? I mean if we have some parallelogram here, what's a parallelogram? It's a figure where those two sides are parallel to each other and those two sides are parallel to each other. With me so far? I am trying to prove that this side length is the same long as that side length, and that this side length is the same long as that side length. The opposite sides of a parallelogram are congruent to each other. That's what we're out to prove. You with me?
Yeah.
Now here's how we're going to prove it. First, consider this diagonal A to C. And notice that that splits a parallelogram into two triangles. And now obviously what am I going to do?
Side.
I'm going to prove that the two triangles are congruent to each other somehow, some way. Okay. Now look at this angle and look at this angle. What do I know about those angles?
They are.
Congruent.
They're congruent to each other. How do I know that they're congruent?
Interior opposites.
They are interior opposites. Here we have two parallel lines, and here we have a transversal cutting across parallel lines. So these two interior opposite angles are congruent to each other. Similarly, we can think about these two parallel lines and view AC as a transversal. And that gives me that this angle is congruent to this angle. And how do I know that those two are congruent? Same thing. They're opposite interior angles when you consider these two parallel lines. You with me? And so, this angle is the same big as that angle. AC is the same big as CA. And finally, this angle is the same big as that angle. And so by angle side angle, I now know that these two triangles are congruent to each other. And since these two triangles are congruent to each other, that side is congruent to that side, and that side is congruent to that side. So now that we see it in the picture, let's just say it completely explicitly. So let ABCD be a parallelogram. Then angle CAD, what's CAD? CAD, this angle, is congruent to angle BCA, this angle. These two angles are congruent to each other. And angle BAC is congruent to angle ACD, or in other words, these two angles are congruent to each other. By, I said corresponding angles, that is not correct. By what? Opposite interiors, I think, is the order that he says it. So, opposite interior angles. By opposite interior. Then, I know that triangle, order here matters. ACB is congruent to which one? So we started at ACB. We went from the double angle to the single angle to the point opposite. Is congruent to CAD. Order there matters very much. By side angle side, just like we said. And so now, AB is congruent to, if we took the two N letters, it's congruent to the two N letters. AB is congruent to CD. What's that? That's these two sides. And BC, so we took those two letters, is congruent to DA, those two letters. Or in other words, those two sides. Good? Or sorry, those two sides for that one. There's a brief. Good so far? All right. Next one. More involved theorem. Theorem 9.1. Here's the setup for this theorem. We have three lines, L, L prime, and L double prime. All three of these lines are parallel to each other. You with me? Our job is to prove that if AB is congruent to BC on some transversal M, then A prime B prime is congruent to B prime C prime on some different transversal K. And it doesn't matter the angle that we would have tipped K at. So I tried to draw those at obviously different slopes so that you could hopefully see that angle doesn't matter. This is obviously longer than that one, right? But if this is congruent to that, then this is also congruent to that. That's what we're proving. You with me? Okay. So I'll set it up. Let L be parallel to L prime be parallel to L double prime, M and K be transversals of all three of those lines, intersecting them at the points A, B, C, and A prime, B prime, C prime, respectively, with AB congruent to BC. Just setting up the picture with those two, or with those 5 lines. With me so far? Okay, what is going to be our proof idea? The idea here is I'm going to make a line parallel to K that goes through A. You with me? We know that such a line exists, and we know that one and only one such line exists from our parallel lines. Here's a line, here's a point not on the line. There exists one and only one line I can draw through point A parallel to K. You with me? So I'm going to sketch that in here. And we're going to call that line K prime. Well, I guess I can just draw it. We don't need it to be dotted. So there's the line K prime. Next thing I'm going to do is I'm going to draw a line also parallel to K through the point B, call it K double prime. Double prime. Right? Okay. Now, notice, here's the big idea. What am I trying to show? I'm trying to show that this is congruent to this. The way I'm going to do it is I'm going to show that this segment to here, I'm going to end up calling this point the point, what am I missing? A, B, C. I'll call that the point D, that the point E. I'm going to show that this triangle is congruent to this triangle. Therefore, this side length is congruent to this side length. And then notice that using these 4 points, we get a parallelogram. And so the opposite sides are congruent. And using these 4 points, we get a parallelogram. So their opposite sides are congruent. So I'm going to show this is congruent to this, but this is congruent to this, and this is congruent to this. Therefore, that is congruent to that, is congruent to that, is congruent to that. Following all the logic there. And ultimately, the whole goal was to show that this was congruent to this. That's what we were after. There's a picture. Now, writing it out. Feel like you understand the picture idea? Okay. So, next are lines. Let K prime through A such that K prime is parallel to K. And let K double prime through B such that K double prime is parallel to K. Let C be the point where K prime intersects L prime. Here's L prime, here's K prime, they intersect at D. We are at C. Let D be the point where K prime intersects L prime.
Okay, yeah, that was
And E where K double prime intersects L double prime. Good so far? Okay. So now notice that angle BCE, this angle is congruent to this angle. How do I know?
They're corresponding.
Those are corresponding angles. Here's two parallel lines, and here's our transversal. So these are two corresponding angles with two parallel lines and a transversal. And we can also say that this angle is congruent to this angle. How are we going to make that argument?
Aren't they also?
Also corresponding angles. Looking at these two as the parallel lines, and this is our transversal.
Oh, you just look at the different.
Right, so looking at K double prime and K prime as our parallel lines, and this line M is our transversal, then these two angles are corresponding angles. Okay. So angle BCE is congruent to ABD, BCE is congruent to ABD, and CBE is the one right here, top, is congruent to BAD, that's one up here, top, by corresponding angles. And then finally, we have triangle CBE. CBE is congruent to what?
BAD.
BAD by angle, side, angle. Angle, side, angle. They have two angles congruent to each other, two sides congruent to each other, and two angles congruent to each other. Therefore, the two triangles are congruent. So finally, I get then that AD, this side, is congruent to this side, since the two triangles are congruent. And by the previous theorem, I get that AD is congruent to A prime B prime, and that BE is congruent to B prime C prime. Right? Finally, putting it all together, I get that A prime B prime is congruent to that, is congruent to that, is congruent to that. Or in other words, A prime B prime is congruent to B prime C prime. Any questions on that one?
On line 5, did you mean say side angle side or angle side angle?
I meant to say angle side angle. Thank you. By angle, side, angle. Good.
Same with line 3 on the previous theorem.
Same thing.
Yeah.
Oh goodness, you guys. All right. Did I mess up anything else?
You can also say that you did equal instead of congruent to the theorem.
Oh yeah, theorem 9-1, the top line, very top.
Good catch. Those definitely are not equal. What does it mean for two segments to be equal? They're identical. They're one and the same. These two segments are not identical segments. They are very different from each other. Okay. Anything else done? All right. So, a couple quick corollaries now of this theorem. What is a corollary of a theorem? Something that follows almost for free. Imagine that the K I started with was in fact K prime. So imagine that the lines I happened to start with both already intersected at the point A. Then if this side is congruent to this side on this triangle, then I already know that this side is congruent to this side. By the exact same theorem. So drawing the picture out for that, first corollary, is if I've got some triangle ABC here, where AD is congruent to DB, and DE is parallel to BC, then I instantly know that AE is congruent to EC. And it just instantly follows from this theorem over here. Here would be our three lines, drawing out the parallel lines for you so that you can see it. Here's a transversal. If one transversal across those lines has its two parts congruent, then any other transversal across those two lines also, or those three lines, also has its two segments congruent. So this is just a special case of this, where A prime and A happen to be the same point. You see that? Okay. The other corollary of this is a little bit more interesting. So we're going to do another corollary here. This time we're going to start with knowing that this side is congruent to that side and this side is congruent to that side. The thing we want to argue is that then this segment is parallel to this segment. So before we were saying if the lines are parallel, then we know that the segments are congruent. The question now is, if we know that the segments are congruent, is it true that these two lines are parallel to each other? That's what we're trying to argue this time. So this time I'm trying to argue if AD is congruent to DB and AE is congruent to AC, then DE is parallel to EC. You see the difference between the two proofs, what we're trying to show? Our different starting point? Okay. So, this one let's actually write out because it's not quite as trivial. So let triangle ABC, let D bisect AB. What does it mean for D to bisect AB?
It means that the two segments that it creates.
It splits them perfectly in half. That's the bisector. It's what splits it in half. So D is the point that bisects segment AB, or in other words, D is exactly the midpoint. Or in other words, AD is congruent to DB. Good? So, let D bisect AB and let E bisect AC. So E over here bisects AC, same thing. What am I trying to show? I'm trying to show that DE is congruent, or is parallel to BC. That's what I'm trying to prove.
On your first line then, did you mean to say EC?
Or two. Red above line one.
DE is congruent to. Thank you. All right. Yes. Keep pointing out the stupid things I say. Good? Trying to show this line is parallel to that line. That's what we're at. Okay. So I've got my 2 points D and E which bisect these, trying to show DE parallel to BC. Here's the way I'm going to do this. I'm going to construct the line through D parallel to BC.
Okay.
And that line that I construct through it is going to intersect AC at some point. We're going to call it F. How do I know it's going to intersect AC?
Is that our triangle one?
Yeah, you guys just proved this on your midterm. If a line comes in and it doesn't intersect BC, how do I know that this line doesn't intersect BC? It's parallel to it. So it doesn't intersect BC. It enters right here. It has to leave on that side. So I know it intersects somewhere on AC.
Wait.
Let's call that point F.
How do we know it doesn't go through one of the vertices? I mean, how do we know it doesn't go through A?
Because it already goes through D and it would be intersecting this line, this segment twice. Good?
Yes.
Okay. So I know that DF is parallel to BC. What am I now trying to argue? That F and E are the exact same point. If F and E are the exact same point, then DF is DE, and DE is parallel to BC. That's what I'm trying to show. I'm trying to show that DE is parallel to BC.
Yeah.
So DF, by construction, is parallel to BC. If F is equal to E, then DE is also parallel to BC, and we're done. Okay. So let L through D, so this is according to what we're constructing now. These lines don't exist in our proof down here. L is this line that goes through there. So let L through D such that L is parallel to BC, and let F be the point where L intersects AC. Okay, what do I know then about AF and FC? I've got a parallel line. I know it bisects this side of the triangle, so what does it have to do to this side of the triangle?
Has to split that line evenly.
It has to bisect it as well. So how big is AF compared to FC?
The same.
They're congruent. So F bisects AC. But E bisects AC.
So they're the same.
So F and E are the same point. Because there's one and only one point that bisects a segment. Okay. So then AF is congruent to FC, which means that F bisects AC. So then F is equal to E. And so DE is parallel to BC. DE. We already knew DF was, and so DE is parallel to BC. Good? Okay. Next. Here is our problem. Here we are, some ancient Greeks. We've got a wall on a temple here. And our job is to put up 6 pillars. So we got to split this up perfectly into 5 pieces. We got to split it perfectly up into 5 pieces. How on earth are we going to do this?
Split it. Wow.
You understand the question?
Yeah.
Yeah.
We have everyone today. Thank you.
Draw 6 parallel lines.
Draw 6 parallel lines where?
Going up. So such that it's
7.
like the previous theorems.
Parallel to what?
A, B, and three.
Or not to AB, but like transversals, or AB is a transversal of all of them.
So we've got a ruler and we got a compass and a straight edge that we can use. So what are you saying to do? You can tell me to draw circles, and you can tell me to draw line segments, and you can tell me to draw lines. And that's what we know how to do.
Do we know how to construct parallel lines?
Do we know how to construct parallel lines? Yes.
Okay.
Can we start with a bisector?
Sure. You want to find the exact middle of that? That's something we know how to do. We know how to bisect. That's pretty easy. Trisect gets a little bit harder.
We're cutting this into 5 pieces.
And splitting it into 5 even pieces. So there's our midpoint. And it'd be nice if we could come up with a procedure that didn't depend on the number 5. I chose that kind of arbitrarily. We kind of want to be able to divide it up into however many we want. Imagine the temple architect comes back to us and says, actually, we're going to use 7 pillars. We found some more marble. And you have to restart from scratch. We want some method we can use. So we're trying to divide this up into 5 even pieces. How do we do that? Ruler, compass, straight edge. Now you might think, oh, I'll just measure it and divide it by 5, right? One, it's kind of hard to measure something. What do we use as our measuring tool? Let's say we had this as our measuring tool. 1-ish, 2-ish, 3, 4, and then some. Now what?
Now you have to
Just smaller.
You gotta
Go
choose
find
a
some smaller
increment,
piece.
Yeah.
And we have to use rounding errors. It can get really messy. And even if we're off by, an inch with a big marble pillar, it could be a problem.
Yeah.
How can we solve this?
What if we create a circle centered at the midpoint?
Create a circle centered at the midpoint. So we create some circle that goes through there. Okay, we got that.
Well, it would go through A and B.
It would go through A and B because it's
Oh, centered at the midpoint.
Yeah.
Sorry.
because A and B are the
So some circle centered at the midpoint, which if I can do a half decent arc, something like that. Okay.
We could put a perpendicular bisector from the circle.
Yeah. We could draw the perpendicular line there if we want. We know that those are right angles. All right. So now that you're thinking about it, at least, let's go over a solution. First thing we're going to do is we're going to start at this point and have someone pull a string. How far? Stupid far. We don't care. So stupid far. Now I'm going to arbitrarily pick some length on my compass and just draw a circle. And I'm going to use that circle. It's the same way that we measure off distances. So I'm going to use that circle to mark off that. I set my compass here, and I draw some circle. Doesn't matter what it was. And it ends there. Now I come here with my compass, and I draw a circle using that point, and I draw it around, and it's going to mark off some other point here. You with me? How many were we after?
5.
So something like that, assuming I drew it half decent. 1, 2, 3, 4, 5, right?
Okay.
Now, who cares what happens from there on out? The nice thing about what we did so far is no rounding errors. Our circle that we used perfectly went into that. How long was our circle? We don't care. The point is we now know that that is as perfectly divided up in 5 pieces as you're going to get. Hard to screw up what we did there.
Yeah.
And that could be exactly pi feet. 3.14159, blah, 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 blah. Who cares? We picked some random length, and we just used it, making sure that our lengths are all the exact same, to the extent that we could make them the exact same.
Yeah.
With me? Now what do? Now we're going to, hopefully I can draw these lines somewhat decent. We're just going to connect this point with this. With me?
Yeah.
So, something like that.
With more string.
Yeah, just pull a string now between those 2 points. That's as easy as can be. Or take your straight edge, same thing as pulling a string, across those 2 points. Now we know how to construct parallel lines. It's a bit tedious, but it's the first thing we did last chapter was show how to construct parallel lines using nothing but a straight edge and compass. And so I can construct a line parallel to this line that goes through this point. You with me?
Yes.
So, we're in trouble here because I can't draw worth anything, but we'll try it. And now I come here and I construct a line parallel to that line through this point. And through here. And through here. Now, since all these parallel lines perfectly divide this up, that's congruent to that, it's congruent to that, it's congruent to that, it's congruent to that, then this is going to be congruent to this, is going to be congruent to this, is going to be congruent to this, is going to be congruent to this. And we perfectly divided it up into 5 pieces. What they asked us to do, 100 pieces. Yeah, that's trivial. Just mark off more pieces, and you have to construct more lines, but that's the process. Nothing special about the number 5 in this construction. Right? So that's how the Greeks did it. They could divide any length up into however many integer pieces you wanted. It's a very easy thing to do. No measurements involved. What is the distance between those 2 columns? The Greeks answer,
Doesn't matter.
who cares? The point is they're perfectly divided up. Okay, any questions on that one? Okay, so we're going to take a small break now from our geometry, and now we've got to start talking about a ratio. What is a ratio? And so we're going to have to do a little bit of algebra, remind you of some stuff from your algebra review that dealt with ratios. First off, just for some fun history, let's talk about that word ratio. Where does ratio come from? What do we mean by a ratio? So if you go back to Euclid's Elements, and when he was trying to say that this segment was, let's say that the ratio of those 2 is 3 to 2. You understand what I'm saying? If this is 2 feet long, then this is 3 feet long. The ratio between them is 2 to 3 or 3 to 2, depending on which way we're going. If you would go read what the word Euclid uses, he says the logos between them is 3 to 2. And logos is a Greek word for reason. The reason between these is 3 to 2. Try and explain what is between them without actually using that word ratio. What do you mean? You might say the proportionality, but we use ratio to define proportionality. So how do you explain what it is? And so you see, Euclid, he's kind of in a pickle. He's one of the first people talking about this thing. He calls it the reason between them. Now, the Latin word for reason is ratio. So in the Latin text, the reason between them is whatever, and so the ratio between them is whatever. And how did the Latins say that something was reasonable? They said it was rational, or the way we now pronounce it, rational. So we still use ratio for reason. In a sense, we say rational. We never say the ratio for the reason. Because this word, now, for some reason, we only use it to talk about this. Even though, through history, it just meant reason. The same way that rational means reasonable. And now, what is a rational number? It's a
Number that-
rationable number.
Yeah.
And so that's where the rational numbers get their name, and that's where ratio gets its name. And for some reason, we don't use it for reason anymore. If I say, what's your ratio? What's your ratio? What? Say, what's your reason? Then you understand me. Okay, so a little bit of history with the word, just for fun. Now, the stuff you won't like as much. Going back to arithmetic in our algebra review, if we were to set up arithmetic the same way that we were developing geometry, in our geometry, we had some undefined terms. Remember some of our undefined terms? Point, line, plane. In arithmetic, there's 0 and 1. Those are undefined numbers. The same way that point is undefined in geometry, 0 and 1 are undefined in arithmetic. We also had an undefined relation, which was, betweenness was one of them, and congruence was another. In the same way that we have congruence and betweenness, in arithmetic we have plus and times in a similar manner. They're undefined. You with me?
Yeah.
Now, with these, we can start defining all sorts of numbers. What is 2? By definition, it's 1 plus 1. That's what 2 means. Notice that 1 is one of those, plus is one of those, 1 is one of those. So, here's our undefined terms. Using nothing but undefined terms, we define a new term. So there's this definition. And now we have 2 defined, we can define 3. What is 3? 2 plus 1. What's 4? 3 plus 1.
It's a
3 recursive definition.
recursive definition.
And so we can go on, and now you can see how we can define all the natural numbers. No, we don't have negatives yet.
Right.
With me?
Yes.
Okay. Now, in your algebra reviews, you were told to use addition to define subtraction. Subtraction is not one of our undefined operations. We actually have to come up with a definition for what that means. So our definition for subtraction was x minus y equals z. What do we mean by that? What did we define that to mean? We meant that to mean x is equal to y plus z. There's its exact definition. Notice everything over here are defined symbols. Everything over here are undefined symbols. And takeaway here is an undefined symbol. So we're now defining it in terms of symbols that we already know. Wait a second. How can I use equals?
It's logic.
That's not one of those.
It's logic.
Equals is more foundational. It's logic.
Yeah.
So every system, whether we're in geometry or whether we're in arithmetic, can use equals. Equals is a concept of logic. It's more foundational. You can use logic in every field of math. So equals is perfectly valid to use here. And you might remember when we did logic, we spent a little bit of time with equals, and we did some basic proofs with equals. Okay, so give you an example of what this definition means. By definition, or not by definition now, but how do I know that 15 minus 7 equals 8? How would I actually prove that? By definition, this means 15 is equal to 7 plus 8. Now, is it true that 15 equals 7 plus 8?
Yeah.
That would be kind of tedious to check, but we could check it. Let me do an easier one that will actually check my hand.
Okay.
Let's pretend that we want to know 4 minus 2 equals 2. And we want to show that. Well, by definition, 4 minus 2 equals 2 means what? 4 is equal to 2 plus 2. Now, is 4 equal to 2 plus 2?
Yes.
Well, we got to check that. Let's really quick do the proof. 2 plus 2 is equal to, what's the definition of 2? 1 plus 1. So this is the same thing as 2 plus 1 plus 1. You with me?
Yes.
Now, we didn't list all the axioms of arithmetic here, because we're not completely developing arithmetic, but there's axioms of arithmetic just like there are for geometry.
Right.
And 2 of them are the commutative property, meaning you can swap the order you add in or multiply in, and the associative property, meaning you can put the parentheses where you want. So this is the same thing as 2 plus 1 plus 1. And by definition, what is 2 plus 1 if we kept writing it out?
3.
3 is 2 plus 1. So this is equal to 3 plus 1. And by definition, 3 plus 1 is going to be 4. If we wrote its definition, we wrote the definition of 2, we wrote the definition of 3. If we continue this pattern, 4 would have been defined as 3 plus 1, and 5 would have been defined as 4 plus 1, etc., etc. So that is equal to 4. And there you go, we proved 2 plus 2 is 4. Make sense? So, here we checked the validity of the statement. And we now proved that 4 minus 2 is in fact equal to 2. Crazy. You now know 4 minus 2 is 2. Those fourth graders got nothing on you. Alright. And now with subtraction, we can start defining some new numbers. I can define negative 1 now to be 0 minus 1. That's negative 1. And I can define negative 2 to be, I could have done negative 1 minus 1 or 0 minus 2. Notice that we already have 2 defined up here, so we can use it down here if we want. I think it's a little bit easier. And in general, I can say negative a is defined to be 0 minus a.
Is there a, so you have a general definition for the negatives. Can you create a general definition for the naturals? Where it's not recursive?
No.
No.
It's going to be using some recursive axiom, however you do it. But doesn't matter. You get the idea so far. We're not doing a deep dive into arithmetic. This is just to give you just a taste.
Yeah.
This is what you would start a real analysis course with. Okay. So there we go. We have our negative numbers. And we define subtraction. Now we're trying to get to ratios. Ratios are using fractions, or what's the operation? Division. So we need to define division. That's what we're out to do. And so, once again, division isn't one of our undefined symbols up here. So we have to define it using our undefined symbols, ultimately. And what are we going to use to define division? Multiplication. And so, by definition, x divided by y equals z. We define that to mean x is equal to y times z, where y is not equal to 0.
Right.
With me? So, when we check that 15 divided by 3 is 5, we would actually validate that 15 is equal to 3 times 5. And if 3 times 5 is in fact 15, then 15 divided by 3 is in fact 5. Make sense? It's a definition of what it means. And so now notice that we can define all of our rational numbers. What is 1/2? It's 1 divided by 2, whatever that is.
How do we go about, so if you have like a fraction, how do we go about proving the multiplication part of that?
How do you mean?
Like, if we have 1/2.
There's an axiom that guarantees us that the result of any division process, as long as we're not dividing by 0, is a number.
That's an axiom?
It's close to that.
Oh, okay.
But the point is, now we have a notion of all our rational numbers. And for the Greeks, this is what was meant by a number. The Greeks had no notion of an irrational number. If you said a number, they were thinking a rational number, and that's all there is to it. And this kind of gives you a sense for why that's as far as they went with their development.
Yeah.
With me so far? Okay. So now we're going to define ratio. The ratio of two numbers, x to y, is x divided by y. That's its definition. Which you probably already would have guessed. But the point is, remind you of that definition from your algebra review, what exactly divide means. Okay, now proportionality. We say A and C are proportional to B and D if and only if A over B is equal to C over D. Your numerators are proportional to your denominators in that order. To write out a more general form saying the same thing to make sure you get the pattern, we could say x, y, z, and w are proportional to x prime, y prime, z prime, and w. If we say that, what are we saying? We're saying x over x prime is equal to y over y prime is equal to z over z prime is equal to w over w prime. That's what it means, in that order. So if I say, let's look at the numbers 2, 4, 8, and 11, and I tell you that these are proportional to 4, 8, 16, what does the last number have to be here to preserve the proportionality? 22. If this one is double that, this one has to be double that, this one has to be double that, this one has to be double that. And if I wrote out the fraction, what am I saying? I'm saying 2 over 4 is equal to, 2 over 4 is equal to 4 over 8, is equal to 8 over 16, is equal to 11 over 22. That's what I'm saying if I'm saying that these are proportional to those. Now, it doesn't matter if I call those the numerators and those the denominators, or those the numerators and those the denominators. It says the same thing. This says 1/2 equals 1/2 equals 1/2 equals 1/2. If I wrote it the other way, I wrote those over those, then it would say 2 is equal to 2 is equal to 2 is equal to 2. Make sense? So it doesn't matter which ones you call your numerators and which ones you call your denominators, but you have to be consistent. If these are my numerators, if this is a numerator, then so are the rest of them. I can't mix and match.
Yeah.
Outside of that, it doesn't matter which way you do it. With me so far? Okay. So let's prove some basic things now about these ratios that we're going to be working with. Remember, why do we care so much about ratios? Remember what it's going to mean for shapes to be similar to each other. Their angles are congruent, and their sides are proportional to each other. That's why we care so much about ratios. Okay, so let's do some basic proofs. We've already done these in the past. I think you had some of them as your algebra review, but let's rewrite them out, write them explicitly, make sure that they make sense. Some basic rules for manipulating fractions that we all know and love. So if b is not equal to 0, so we're not dividing by 0, if b is not equal to 0 and c is not equal to 0, then a over b is equal to a times c over b times c. Or in other words, if you have a fraction, you can multiply the top and bottom by the same thing and it doesn't change your fraction. Right? If I have 1/2, that's equal to, multiply the top by 4, multiply the bottom by 4. 1/2 is equal to 4/8. That's essentially what we're showing here. Understand what it is we're trying to prove? Okay, so let's prove it. So let a, b, and c such that b is not equal to 0, c is not equal to 0. And I'm going to let x equal a over b. Whatever a over b is, let's call it x. What am I trying to show? X is equal to a times c over b times c. I know x is equal to a over b. I'm trying to show x is equal to a times c over b times c. Because I'm trying to show a over b is equal to a times c over b times c. So I got a equals this side, or x equals this side. I need to prove that x also equals this side, and we're done. Good? Now, what does it mean for x to equal a over b? What is that precise definition?
They're identical.
No.
Oh.
If z is equal to x over y, then that means x is equal to y times z.
Right.
If x is equal to a times b, then that means that the numerator is equal to the quotient times the denominator. Or in other words, it means that a is equal to x times b. That's the exact definition. Your equality, just move the y over here. If numerator divided by denominator equals quotient, that means that numerator is equal to denominator times quotient. If x is equal to a over b, then a is equal to x times b. That's its exact definition. Now, we're going to go back and use a rule of logic. This is not a rule of arithmetic, it's more foundational than that. What was the rule of logic? The rule of logic was that if a is equal to b, then for any operation, it doesn't matter what it is, a, that operation times c, is equal to b, that operation times c. If this is the case, then this is always the case. And we check this with, remember our two rules for using identity? Our first rule of identity is everything's equal to itself. And our second rule is equals substituted for equal. Equals can always be substituted for equals.
Yes.
So I have this, I'm trying to prove that this is the case. How do I prove it? If I know that a is equal to b, then I can substitute that down here for this b. So I know this gives me a sum operation c is equal to b, or is equal to a sum operation c. And is this always true? Yes, because everything is identical with itself. Maybe think about this backwards. I know that this is always true. Now substituting equals for equals gives me this is true. So if this is the case, then this is the case. And here's the middle piece of logic you use to prove it. Okay, so now we're using that thinking in our proof. If I know that a is equal to x times b, then A operation number is equal to this operation number, that same number. The operation I'm using is times. Down here, that circle meant any operation as long as it's defined. Didn't matter what it was. Could have been plus, could have been times, could have been divided by, could have been subtract. It's why you can always do the same thing to both sides of an equation, and it doesn't change it. That's using logic. So using that logic, we multiply both sides by C. So that's how we get from here to here. You with me? Now, just use commutativity and associativity. So I'm just going to rewrite out this side. I'm going to write the x first times the b times the c. Oh, so that's just associativity. You with me? And so now, if this number is equal to that number times that number, numerator equals quotient times denominator gives me that numerator over denominator is equal to quotient. This is the exact same thing as this piece here.
Yeah.
Using this definition, just going the other way.
Right.
I have left hand equals the product of two things. Then, the way you're told this is divide both sides by the y, and it gets you here. So going from here to here, what do? We divide both sides by b times c. And so I'm left with x is equal to a times c over b times c. But it's using that definition. I'm going backwards from this to this.
Right.
You see it?
Yeah.
That becomes our numerator. The thing we're moving becomes our denominator. So I know that a times b is equal to x. And I just showed that x is equal to a times c over b times c. Or in other words, a over b is equal to a times c over b times c. Proof makes sense? Not bad? Okay, next one. We're going to prove that a over b is equal to c over d if and only if a times d is equal to b times c. You were told this in terms of cross multiplying. That's how you solved it. If you had something like 2x over 15 is equal to 9 over x or whatever, you were told cross multiply and rewrite it like this. We're going to prove cross multiplying in fact works. And then you could also go backwards. You could go from this to that fraction if you wanted. All right, let's prove it. So this is the case. A over b equals c over d if and only if a times d is equal to b times c, where b and d are not 0. Because we can never divide by 0. It's undefined. Good? Okay, so we're going to prove, well, first off, let a, b, c, and d be numbers such that b is not 0 and d is not 0. Okay, now an if and only if proof, so I got to show that this being true implies this is true, and then I got to show that this being true implies this is true. So we're going this direction first. So assume that this is true. Assume a over b is equal to c over d. With me? Now, whatever a over b is, I'm just going to call it x. So what is x? It's a over b. Now, since a over b is c over d, then x is also equal to c over d. So now, I'm just going to use this definition twice. If I know that x is equal to a over b, then what do I know? I know that a is equal to x times b. If x is equal to a over b, then the numerator is equal to the quotient times the denominator. Similarly, if x is equal to c over d, then the numerator is equal to the quotient times the denominator. With me? All right, now what was I trying to prove? That's just using my given information. What am I trying to prove? I'm trying to prove that a times d is equal to b times c. So let's figure out what a times d is equal to. So then a times d is equal to what? Well, we know what a is, right? So just plug in what we know a is. A is the same thing as x times b. So a times d is the same thing as x times b times d. You with me? Now I'm just going to shift these terms around a little bit and move my parentheses using commutativity and associativity. So I'm going to put the b out here in front, boop, and I'm going to group the x and the d together. You see how I went from here to here? It's just moving around the terms. 2 times 3 times 5 is the same thing as 5 times 3 times 2. Doesn't matter what order you multiply in. Okay, and finally, what is x times d?
C.
It's the same thing as c. So it's the same thing as b times c. So I just already showed that if this is the case, then a times d is equal to b times c. And I had to use that given information.
Okay.
Make sense? Now we gotta go the other way. I gotta prove that if A times D is equal to B times C, then A over B is equal to C over D. So go in the other direction now. You with me? Okay. So let's assume that A times D is equal to B over C, or B times C. I need to prove that A over B is equal to C over D. That's what I'm trying to prove. With me? Okay. So I know that A over B is equal to A times D over B times D. How do I know I can go from here to here?
Sorry.
The previous theorem. Just using the previous theorem up here, the previous theorem says, if you've got a fraction, you can multiply the top and the bottom by the same number, and you're good. I got a fraction, multiply the top and the bottom by the same number, call it B. Alright, now, what did we assume? What is A times D?
B times C.
It's B times C. So going from here to here, I just replace the A times D with the B times C. You with me? Now, notice that I can cancel out the B, top and bottom, leaving me with a C over D. How do I know I can cancel out the bottom B, the B, top and bottom?
Because of the first.
The previous theorem, it's just going this way.
Yeah.
If I know that A times C, well, I know that A times C over B times C is equal to A over B. This, reading it this way, says you can cancel out the same thing top and bottom. Reading it this way says you can multiply the same thing top and bottom. You can do both those. So reusing that previous theorem once again gets us here. And so there's a method to the order you prove these things in. Make sense? Okay. So there's our algebra review, algebra reminder. Shifting gears back now to the geometry. That was just stuff that you should have already covered from your algebra reviews, but you probably didn't remember all that. Okay. Now in geometry, what do we mean by the ratio of two sides? What do we mean by the ratio of a segment AB to CD? By definition, the ratio of AB to CD is the number. Notice that, what is AB?
Segment?
Yeah, but what number is it?
It's not.
Bad question. It's a segment. It's a geometric figure. It's not a number. So how do I talk about the ratio between two geometric figures? How do I get numbers from figures?
Take their length.
You take their length. So the ratio of AB to CD is the number, the length of AB, which is a number, divided by the length of CD, which is a number. AB, not a number. The length of AB, that is a number. The length of CD, that is a number. And now a number divided by a number is well defined. And there's like one teeny tiny gotcha here. C and D can't be the same point. Because if C and D are the same point, what is the length of CD?
0.
0, which you can't do. So don't talk about proportionalities between a segment and a point. It doesn't make sense. It has to be between two segments.
Makes sense.
Okay. And similarly, when we say that a triangle ABC is proportional to a triangle A prime B prime C prime, what are we saying? We're saying that the length of AB over the length of A prime B prime is equal to the length of BC over B prime C prime is equal to the length of AC over A prime C prime. So if these two triangles are proportional to each other, pretend I drew this one 3 times as big as that one. That means that if this divided by this is 3, then this divided by this also has to be 3, and this divided by this also has to be 3. That's what it means for them to be proportional.
If a triangle is proportional, will it have the same angle congruency?
If two triangles are proportional to each other, will all their angles be congruent? And the answer is yes. I think. I'd be really hard pressed to see how it could be the case. So, my gut is yes. We know that the converse is the case though. If all the angles are congruent, then they are for sure proportional. And we'll be proving that. Will we prove the converse? I'll have to think about that. Okay, this was nothing. This was scribbling examples from before. So, there we go. We have our definition of proportionality. Any questions so far? Oh, let's go over there. Good? All right, next board. That is not all going to fit. But we don't need it all to fit because we don't go past that. Okay, that's fine. All right. So our next theorem here, we are going to prove that the ratio between two sides, when I talk about the ratio of two segments, then that's talking about the lengths of the segments, right? But if I'm going to measure the length of something, what do I need? Suppose you ask me what's the length of this room, and I say, oh, it's 6.
What?
6 what? You need a unit.
Or metric.
Well, a metric is a function. What we need is a unit. So, the ratio of A to B, AB to CD, the question is, that means that if I talk about the ratio of two segments, how do I know what units to use?
Doesn't matter as long as they're the same. You use the same unit for everything.
And that's what we're going to prove is the unit you choose doesn't matter. Let's say I measure one distance, and it turns out that it is 6 kilometers. And I measure some other distance, and it comes out to 2 kilometers. Question, what is 6 kilometers over 2 kilometers equal to?
3 kilometers.
3.
It is just equal to 3. Kilometers cancel out top and bottom. There are no units that show up over here.
Gotcha.
Imagine that I said, well, okay, that's all well and good with kilometers, but what if we use meters? Well, if we use meters, then the top would have been 6,000 meters over 2,000 meters, if we would have measured it with meters instead, right? Meters cancel out top and bottom. Divide top and bottom, all the zeros cancel out. You're left with 6 over 2 or 3. It still comes out the exact same thing.
Yeah.
Not 3 meters, not 3 kilometers, just 3. It's just a number. A ratio is just a number. It doesn't make sense to put units on it. If I say the ratio of that wall to this wall is 2 to 1, that means that wall is twice as long as this wall. And I say, well, you don't know that. You have to measure it. If I know the ratio, the units don't matter.
Right.
So that is what this proof is saying. The ratio of AB to CD is a constant. In other words, it doesn't change. It doesn't matter what your units are. So we're going to prove that units don't matter. Go ahead.
This is theorem 9.4. Where did 9.2 and 9.3 go?
Sorry. Any other questions? All right. So, let's prove this. So, what we're going to do is let EF and GH be any two units. I'm going to show that the ratio of AB to CD is the same in both those units. So if the ratio is the same for any two units you choose, then it's always the same. You with me? So pick two random units, doesn't matter what they are. One could have been inches, one could have been kilometers. I'm going to pick two random units, doesn't matter what they are. I'm going to prove that the ratio is the same with both those units. Okay, so let EF and GH be any two units. Now we take unit, EF, and we measure AB. So I'll draw a picture here just to help us think about it. Let's pretend that here's AB, here's CD, here is EF, and here's GH. There's all our segments. You with me?
Yeah.
Now we're going to say that the length of AB, when EF is our units, comes out to M. In my picture, it came out exactly to 4. It didn't have to come out exact. It's just nice for the picture to help you follow. So we're going to say that measure AB, whatever it is, we're going to call its length M, some number. Measure CD with that same unit, and we're going to call it N. In my picture, M was 4 and M was 3, where EF was our unit. With me so far? Now, let the length of EF be K, where GH is a unit. So now if GH is a unit when I measure EF, then GH goes into EF how many times? In this case, 4 times. But in general, let's say it goes into it K times. Question. How long would AB be? How long would this segment be if I used GH as my unit? Well, in the concrete case I have written out here. Let's say that EF is exactly 4 GHs, and AB is exactly 4 EFs.
16.
So it would be 16, right? It would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, if I were measuring with that length there.
We proved that, didn't we?
Yes,
I feel like we proved this before, yeah.
we did prove it.
Okay.
Didn't want to. Thought it was better to redraw the picture. You with me? So the length here, if the length here is 4, when this is our unit, then the length up here, this thing's length is going to be m times k when this is our unit. Or in other words, 16. You with me? Similarly, the length of CD was 3 when this was our unit. So what is the length of CD going to be when GH is our unit? 12. And how did you get that? You just called that n times k. Right? Let's do one more concrete example. Let's say that this marker lid is exactly 1/5 of this marker. And I measure out this wall, and this marker goes into this wall exactly 25 times. You with me?
Yeah.
How many times would the marker lid go into the wall?
125.
125 times. If there's 5 marker lids to a marker, and the marker went into this wall 25 times, then the marker lids would have gone into it 125 times. Same concept. So that's all we're saying here. So if the length of AB is m and CD is n, with EF as our unit, and EF is k, GH's, then the length of AB, when we use GH, is going to be m times k. And the length of CD, when we use GH, is going to be n times k. When, not EF, but when GH. When GH is a unit. Make sense? Now finally, let's look at the ratio. What is the ratio? Well, one of the ratios, AB over CD, was m over n. We got m over n when we used this unit. And when we use this unit, we got m times k over n times k. But what did we just barely prove over there? If you've got a k in the top and the bottom of a fraction, you can cancel them out. And so, the ratio using a different unit gives us the exact same number as the ratio of a previous unit. So units don't matter. The ratio always comes out the exact same. Make sense? Okay. Now, definition of commensurable. What does it mean for two segments AB and CD to be commensurable? Intuitively, it means that we can find a small enough length to perfectly go into both of them. Let me tell you what I mean. Let's say that I have a length here and a length here, and I want to measure them. Let's say I use inches, and I count off inches. And when I count off inches, 1, 2, 3, 4, 5, 6, 7, 8, and let's pretend that was a little bit longer, 9. Let's say inches perfectly went into that. But when I came to count this off with inches, we got 1, 2, 3, and then some extra. So inches perfectly went into this, but it didn't perfectly go into that. So I might say, okay, inches was too big. Let's try centimeters. And I try centimeters, and let's say centimeters this time perfectly goes into this one, but it doesn't perfectly go into that one. Question, is there always some small enough length I can use that perfectly goes into both of them? Maybe centimeters doesn't work. Maybe, I don't know, would nanometers work? Maybe we use widths of atoms, right? Count how many atoms, 1, 2, 3. Is there ever a small enough length that we're guaranteed it perfectly goes into both of them? And the shocking, crazy answer is, of course there is.
That's exhausting.
Just kidding.
No.
The answer is no. And it's a shocking answer. This blew the Greek spines.
Well, you have a rational number.
Yeah, it leads to irrational numbers. Let me give you the example. The example is, if I take a square, and I construct a square so that this side length is 1 meter, and this side length is 1 meter. Question, What is the length of this side?
The square root of 2 meters.
It's exactly the square root of 2 meters. How is he getting that? We haven't covered the Pythagorean theorem yet, but that's what he's using. If I notice that this is a right triangle, if I've got a right triangle here, and I know that this side length is 1 and this side length is 1, then this side squared plus this side squared equals this side squared. So this is equal to, I know that 1 squared plus 1 squared is equal to, call this side x for now. 1 squared plus 1 squared is equal to x squared. What's 1 times 1?
1.
1. 1 plus 1 is 2. So 2 equals x squared, or take the square root of both sides, and I get x is equal to the square root of 2. So this side length here would be the square root of 2. And it turns out, well, so intuition for what it means for two things to be commensurable is there's a small enough length you can find that measures both of them. Now that's not its precise definition. We'll see its precise definition here in a second. But it gives you good intuition for what it is. And it turns out that two lengths being commensurable, finding a measurement that perfectly goes into both of them, is the same thing as them being rational. Their fraction, their ratio being rational. Being able to express it as an integer over an integer. Why? Because, think about it, if I found something small enough that perfectly goes into this and this, then the length of this would be exactly m of those, and the length of this would be exactly n of those. And now I could say that the square root of 2 is equal to your ratio here. N over n, right? And so the square root of 2 being rational is the same thing as there being some measurement that goes into both of those. And the Greeks proved that the square root of 2 was not rational. Now that's not quite how they said it, because keep in mind, what did a Greek mean by a number? They meant a rational number. So what they actually, the way that they say their discovery is, this isn't a number. That was disturbing. Here's a length without a corresponding number. There is no number you can assign to that length. Because there's no way of counting both these things.
Right.
Very disturbing. You might wonder, why is it that the Greeks went crazy with geometry and hardly did anything with algebra? And here's part of it. Geometry can talk about things that algebra just can't. Is the way that they saw it. How hard was it to construct that length? Piece of cake. Take a square, take a diagonal. And yet it's not a number. And so geometry seems to somehow be more powerful than algebra. It can talk about quantities that algebra just can't. Is the way that they saw it. Now today we just say, no, it's a square root of 2, it's a number. We go on our merry way, and we already had that whole conversation in this class, right? So, that's a side note with the square root of 2. Anyways, so what does it mean for A, B, and CD to be commensurable? I told you intuitively it means some length can perfectly go into both of them, but that's not the exact definition. What it means is that their ratio is a rational number.
Right.
Now, do you remember what a rational number is?
It's a number that can be expressed as a ratio.
It's just an integer over an integer. So not just a ratio.
But not
It's what the Greeks thought of as ratios, is what a rational number is.
Oh.
Because here's a perfectly fine ratio. Okay, there's a ratio, but that's not a rational number. Because it's not an integer over an integer. It's what the Greeks thought of as ratios, not ratios in general.
Okay.
It's a ratio of integers. So, what are the rationals? They're any integer over an integer you can write. Like 4 over 19. Like -7 over 13. What about pi over 2? No, pi is not an integer. So, two side lengths, or two segments are commensurable if and only if their ratio is a rational number. It can be expressed as an integer over an integer. With me?
Yeah.
Okay. So next theorem here, we're going to prove that AB is commensurable with CD, those two segments are commensurable, if and only if there exists some unit, EF here is just going to stand for a unit, such that the length of AB is exactly m, and the length of CD is exactly n, where m and n are integers. Now, this is what I gave you as the intuition for commensurable. Now we're going to prove that if they're commensurable, then that intuition works, and vice versa. So, we're going to prove that two numbers are commensurable if and only if I can find some length small enough that it perfectly goes into both of them an integer number of times. Like it perfectly goes into one 5 times and the other 7 times. None of this, it goes into it 4.5261788, whatever, inches. Make sense what we're trying to prove? So if and only if, so we're going this direction first. So, we're going to start by assuming that AB is commensurable with CD. What does it mean for AB to be commensurable with CD? What's the exact definition?
It means the ratio is in rationals.
It means that the ratio is irrational. Right?
Yeah.
That's the exact definition. So let's assume that AB's length over CD's length is a rational number. Now what does it mean for it to be a rational number?
It's fraction of
It can be an integer over an integer. Not that they are both integers, but that they can be expressed as integers over integers. Let me give you an example, because this is a little tricky. 2 times the square root of 2 over 4 times the square root of 2 is rational, because it can be expressed as an integer over an integer. In this case, cancel out that top and bottom, divide top and bottom by 2, and it's exactly 1/2. So it's not that the numerator is an integer, and it's not that the denominator is an integer. It's that the numerator over the denominator can be expressed as an integer over an integer. Little bit of nuance there. Little tricky. With me so far? Okay. So assume that AB over CD, its ratio, is rational. That means that there exists 2 integers out there, m and n. Remember that this z is your symbol for integers. So reading this precisely, assume the length of AB over the length of CD is in the rationals. That ratio is in the rationals. That implies that there exists m and n in the integers such that AB over CD is equal to m over n. This could be the length of AB, this could be the length of CD, this could be our m, this could be our n. It is not necessarily the case that this is equal to m. You can't just say that. Okay. Now, we're going to pick a unit. I need to come up with a unit that goes into AB exactly m times and goes into CD exactly n times. I need to find some unit that goes into both of them an even number of times. No remainder. So I'm going to let my unit, EF, such that its length is just 1/m of AB. So if this is my segment, AB, and m, we know that m is going to be some integer, like 4. I'm going to pick EF, so let's pretend m was 4, let's pretend, what was our other segment, CD? And n here for it was 3. So AB over CD, I am going to pick EF here, so that its length is 1/m of AB. So EF is exactly 1/4, in this case, of AB. So here is EF. It's a segment that long. Here's EF. You with me? Now if that is EF, what is the length of AB in terms of EF? 4, but in general it's just n. If I choose my unit, let EF such that the length of EF is exactly 1/m of AB. If EF is exactly 1/m of AB, question, how many times does EF go into AB? M times. If I'm going to define a new unit, call it Shaw, and I define one Shaw to be exactly 1/5 of this room, how many Shaws is this room? 5. If by definition it's 1/5 of the room, then there's 5 of them in the room. By definition, I'm choosing this unit such that its length is exactly 1/n of AB. So then, the length of AB has to be m. And if the length of AB has to be m, then the length of CD has to be n. because I know that, maybe do a little bit of algebra to the side, I know AB over CD, whatever those numbers are, is m over n. Now if I know that AB, I choose a unit so that the length of AB is exactly m, then the length of CD has to be exactly n. And we can finish out the algebra from this if we want. Using our theorems over here, we know if we have two fractions equal, then their cross multiplication has to be equal. So that tells me that this times this has to equal this times this. So I get m times n has to equal m times CD.
Right, and then you can just cancel out the m's.
And then cancel out the m's both sides, and you get n is equal to CD. In case it wasn't just obviously jumping out to you, how if AB is exactly m, then CD has to be exactly n. Okay, there we did it. We showed that if these two were commensurable, in other words, we showed that if their fraction was if their ratio was irrational, then there exists some unit of length that perfectly goes into both of them with no remainder. Now we need to show the converse. I need to show that if there exists some unit that goes into AB exactly m times and CD exactly n times, where m and n are integers, then A and B are commensurable. Or in other words, the ratio of A to B is a rational number. So proving that direction now. So let EF be our unit. We found some unit small enough that it perfectly goes into AB exactly m times, where m's an integer, and it perfectly goes into CD exactly n times, where n's an integer. Maybe something like 5 and 7 here. Who knows? With me so far? Then, the ratio of AB to CD is just m over n, which is an integer over an integer, so it's rational. So then they're commensurate. So the second direction, super trivial. The first direction is the interesting one. Good? Okay. So with that, we are now finally for our definition of what it means for two triangles to be similar. Triangle ABC is similar to triangle A prime B prime C prime.
That's the symbol for similar.
Oh yes, thank you. It's just the tilde symbol. It's like the top of the congruence without the equal part. Okay, so triangle ABC is similar to triangle A prime B prime C prime if and only if angle A is congruent to angle A prime, angle B is congruent to angle B prime, and angle C is congruent to angle C prime, and the length of AB over A prime B prime is equal to the length of AC over the length of A prime C prime is equal to the length of BC over the length of B prime C prime. Or in other words, all their sides are proportional. Now this definition generalizes to convex polygons in general. Remember what a convex polygon is?
One that its polygonal path doesn't cross itself.
That was for a regular polygon. A convex polygon, the intuition for it, is that any segment you draw connecting two sides never intersects another side. There's a convex polygon. Let me give you a non-convex polygon. Notice that I could draw a segment connecting these two sides, and it intersects like that. So this definition works for all convex polygons as well, not for polygons that aren't convex. And we won't be dealing with any that aren't, so don't worry about it. So two convex polygons, so now this would be something like this, and then try and draw one similar, we're in trouble. Something like that. So two convex polygons are also similar, provided that all their angles are congruent to each other and all their sides are proportional. That's what it means in general. So two convex polygons are similar if and only if their angles are congruent and their sides are all proportional to each other. Make sense? Okay. Now, our last theorem, which is how you were told to think about similar triangles. You were told throughout school to think about similar triangles as all their angles are congruent. And you never thought about their sides being proportional to each other, you just checked the angles. We're going to prove now that if the angles are congruent to each other, then the sides are proportional. In the special case of a triangle. This is not generalized. So, let triangle ABC and A prime, B prime, C prime, such that angle A is congruent to angle A prime, angle B is congruent to angle B prime, and angle C is congruent to angle C prime. We are going to prove that triangle ABC is similar to triangle A prime, B prime, C prime. With me so far? Scribble our picture to the side here. Here's A, B, C. Here's A prime, B prime, C
Did
prime.
you make congruency with the angle B?
Probably. Oh my wow. Yes, these angles are not the same.
Okay. Just checking.
Okay, so here's a triangle, here's a triangle. Ignore the green, only focus on the black for now. What do I know? I know that this angle is congruent to this angle. I know that this angle is congruent to this angle. And I know that purple. This angle is congruent to this angle. I'm trying to show that this triangle is similar to this triangle. The blue didn't really show up there, did it? With me so far? Just setting out the basic picture. What is our proof idea going to be? I'm going to construct a triangle at the top of this bigger triangle, such that this one is congruent to this one. I'm going to show that the big triangle is similar to the small triangle, and therefore similar to this. So throughout the process of my proof, I'm going to construct a triangle here that's the same as this, so that the big one is similar to the small one, and then therefore the big one is similar to this. And that's going to be some of the flow of my logic here. You with me? So that's what the D here and the E here are going to be for the points to remake that triangle. Okay. One more thing that I'm going to assume is that A prime, B prime, and AB are commensurable. Now, this is not a warranted assumption, and it is not in general true. It is just a super pain to deal with lengths that aren't, and would require us to use limits, which we don't have in this class. So it is true even when they're not commensurable, but we're going to assume that they're commensurable in the proof because, frankly, we don't have the tools to deal with it when they're not. So it's true in general, but we're only going to prove a special case to give you a feel for how the proof goes. Make sense? Okay. So let's get started. So without loss of generality, let AB be greater than or equal to A prime, B prime. Or in other words, we're going to call ABC the bigger of the two triangles. What if this triangle happened to be bigger? Relabel everything. So call the bigger triangle ABC and the smaller triangle A prime, B prime, C prime. If they're both happen to be the exact same size, then it doesn't matter which one we call AB and which one we call A prime, B prime, C prime. Because then they're congruent, and so obviously they're similar. With me so far? So let AB be reference whichever triangle has the longer side, whatever's bigger out of AB, A prime, B prime. We'll call that one AB. And assume that AB and A prime, B prime are commensurable. Here's where I'm saying we're only proving a special case. This is not a warranted assumption, but we don't know how to handle it when we don't make this assumption, so just a special case. With me so far? Okay, now what does it mean for these two lengths to be commensurable?
Their ratio is,
Well, we'll go exactly to where you're saying. So, it means that their ratio is a rational number, which we also proved means that there exists some small enough segment such that it goes into A prime, B prime exactly m times and AB exactly n times, where m and n are integers. You with me? So, whatever these two side lengths are, I know that there exists some segment out there. Let's get rid of some of the noise here. I drew the segment right here. There exists some segment out there, FG, such that FG goes into A prime, B prime, exactly m times. In our concrete case, m happens to be, how many times does FG go into A prime, B prime? 3 times. And it goes into this side exactly how many times? As I drew it out, 7 times. So m is 3, n is 7 in the picture I have drawn here. Over here, m and n are just some integers. We don't know what they are. This could really be 15. That could really be 97. But for our picture, I drew a concrete case for m is 3 and n is 7. With me so far? Okay. So, since they are commensurable, there must exist some segment out there such that using that segment as our unit, it goes into a prime b prime exactly m times, and it goes into ab exactly n times. Now, since I know that AB is the bigger of the two, I probably should have handled the special case where AB is exactly equal to A prime B prime. Obviously, two congruent triangles are similar to each other because the ratio of all their side lengths is exactly 1. So we're only going to handle the case where AB is greater than A prime B prime. We won't handle where it's equal. Okay, so now if I know that AB is bigger than A prime B prime, what does that mean? It means that there exists some point D such that AD is congruent to A prime B prime, where D is between A and B. That's the exact definition of what it means for AB to be greater than A prime B prime. I can find a point D such that AD is congruent to A prime B prime, where D is between A and B. With me? So, let D be the point in AB and E be the point in AC, such that AD is congruent to A prime B prime and AE is congruent to A prime C prime. Setting up this picture, all the black so far. Good so far? Okay. Now, last thing to notice is that by side angle side, this triangle, ADE is congruent to A prime B prime C prime. Because I constructed it such that this length from A to D is exactly congruent to this length from A prime to B prime. And similarly for this length over here is congruent to that length over there. So by side, angle, side, then this triangle I constructed ADE is congruent to A prime, B prime, C prime. You with me on that? Okay. So we've got that so far. Now, what am I going to do? We're just trying to fill it in. Okay. So now what am I going to do? My goal now is to show that triangle ADE is similar to triangle ABC. You with me? Now I know that this angle is the same big as that angle because this triangle is congruent to this triangle. And similarly, I know that this purple angle is congruent to this purple angle.
Because they are.
Because this is congruent to this, and it was given that these angles are congruent to these angles. Not even using corresponding angles.
No.
You're jumping to where I'm trying to go. Rather than, see, you want to say that's parallel to that, and therefore the angles are congruent. We're going the other way. Since I know that these angles are congruent, I now know that this is parallel to this. It's the reverse logic. It's how we constructed parallel lines. So, make it very clear. By construction, that angle were congruent to that and that. And it was given that that and that are congruent to that and that. Therefore, that's congruent to that, and therefore that's congruent to that. And that's how we know that this line is parallel to that line. So I'm given that those are now parallel. You with me? Okay. So now, what do we do? The next thing we do is, since AD is congruent to A prime, B prime, we now know the length of AD. What's the length of AD?
Is compared to A prime, B prime.
It's congruent to A prime, B prime, but what was the length of A prime, B prime? We already measured it.
3.
In this case, it was 3, but in our proof over here, it's
N.
M. So now I know the length of AD is M. And then just reminding you, the length of AB we already knew was N.
Right.
With me? Okay. Now we're going to mark off the points that we would have used to measure these. Remember, measuring is a physical process of taking your segment and marking it off over and over again. That's exactly what it means to measure those things. And so we're going to mark off the points A1, A2, AN that measure AB. And we're going to mark off the points. So A1, A2, A3, A4, A5, A6, A7. These are the points that measure off AB. How many A's must there be if I know that the length of AB is N? Then there must be A1, A2, all the way to AN. Whatever our last point is, A sub 7, is however big N is. What did it mean to say that the length of AB was N? It meant that our segment went into AB exactly N times. That's what we're doing. We're just using A to mark off those segments. That's what the sequence of points A does. You with me? Yeah. So, I know that A1, A2, all the way down to AM gets me to exactly D, and all the way down to AN gets me to exactly B. That's what meant for AD to be 3, and AB to be 7, or AD to be M, and AB to be N. Okay, so I'll mark off all those points. Now what am I going to do? Notice that, how big is this distance compared to this distance? It's the same. And how big is it? It's exactly FG. Just physically measuring, that's where those points are coming from. Okay, so now I'm going to construct parallel lines to BC. I'm going to construct parallel lines to BC through each of those points. You with me? And they're going to come out over here and mark off the points where they intersect as B. Now, since we had an A1 here, the point that it goes over here, the line through A1 that intersects over here, we're going to call B1. And through A2, we're going to call B2. And through A3, we're going to call B3. A4 to B4, etc. With me? All those lines are parallel. So if I know that this length is congruent to this length, how does this length compare with this length? It's also congruent. So the point is that I know that this segment is congruent to this segment, is congruent to that, is congruent to that, is congruent to that, is congruent to that, is congruent to that. So when I use this now as my unit over here, how many times does it go into AE? M times. And how many times does it go into AC? N. And so notice that, what was AD over AB? AD over AB, in terms of its length, was exactly equal to M over N, where this was our unit.
Which is...
Now pick this as our unit, whatever that is, B1 to B2, I think is what I say in my proof. Pick that as our unit. Doesn't matter which one of these segments we choose, just pick one of them. Pick B1 to B2 as our unit. Now what is the length of AE? How many times did this unit go into AE? M times. And what was the length of AC? N. And so we got that the ratio of this side to this side is exactly equal to the ratio of this side to this side. And now we can reconstruct our proof, this time putting our triangle down here and constructing all our parallel lines this way to show that the ratio of this to this is also equal to the ratio of this to this. But that's what we were trying to prove. We were trying to prove that the number that AD over AB gives you is exactly the same number that AE over AC gives you. So we need to find some unit length that went into AE exactly M times and went into AC exactly N times. And the unit length we found was this B1 to B2. So there's explained it all. Let's read it in the words one more time to make sure it makes sense. So mark off the points A1, A2, dot, dot, AN, that AB measures, or that measure AB, when we were using, maybe mark our segment, our unit over here. Over here with the A's, we are talking about using unit FG. That's our unit. So mark out the points A1, A2, AN, that measure AB, and construct lines through each point parallel to BC. So all our lines, all parallel to BC. Okay. Now let B1, B2, dot, 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 Bn be the points where they intersect AC, each of those lines. And note that from B1 to B2 is congruent to B2 to B3 is congruent to B3 to B4, dot, 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 all the way down. How do I know that all these lengths are congruent to each other? That's going all the way back to this first thing right here. If they're congruent on this side, then they're congruent on this side. And so finally, then picking one of those segments, I chose the segment B1 to B2. Then using B1 to B2 as a unit, the length of AE was exactly M. And the length of AC was exactly N. Therefore, the length of AD to AB, which was M over N, is exactly the length of AE to AC. And now finally, since AD is congruent to A prime B prime, if two things are congruent, then what? They have the same length, right? So, the length of AD is the exact same thing as the length of A prime B prime. And the length of AE is exactly the same thing as the length of A prime C prime. And so I showed that A prime B prime over AB, those lengths, is exactly equal to the length of A prime C prime over the length of AC. So we only proved, so far, that the ratio of this side to this side is perfectly equal to the ratio of this side to this side. We're not going to prove the third case because it's just repeating the proof. And just constructing the parallel lines this way. And making for each point we have over here, we mark a corresponding point on this side. And it's going to measure it off the same way. It's the exact same construction we used over here, dividing things up. Well, not the exact same, but the exact same idea. Since I have this perfectly split into m and n pieces, I can then construct lines that perfectly split this into m and n pieces. Make sense? Okay. So that is it for what we're going to cover for today. We're splitting chapter 6 into 2 pieces, so you have your first half of chapter 6 homework. We'll finish chapter 6 next time.
Chapter 9.
Chapter 9, thank you, not chapter 6. Yeah, you remember, we are past chapter 6, right? That was a big one. We're done with chapter 6. So next week's lecture will be shorter. We covered most of the chapter here today, so we've covered more than everything you need to do for your homework. You only have to do what's on your syllabus. Want to cover a little bit extra so that we have time to actually check homework next time and keep up on homework as we go. So be ready to check homework next time. Sorry, any questions before I turn off the camera that you want recorded? Great. You have the rest of class to start on homework.